Okay, so let me turn my video on. Welcome, everyone. Thank you for coming. This is the first of 6 sessions, 2 for each committee associated with each of the 3 core community surveys to discuss where they are in the process of defining the surveys. The success of Roman's observation program depends not only on the hard work of the committees, for which I'm very grateful, but also on the active and proactive engagement on the part of the community. So I'm happy that you have the opportunity to see where the committee are in their deliberations. I hope that you take this as an opportunity to provide comments and feedback. And I'll leave you simply with my thanks to the committee for all their hard work and to the community at large for providing so much great food for and thought in coming up with the committee deliberations so far. Okay, let's go.
Okay, let me share my slides. All right, does it look okay? Can I get a thumbs up from someone? I only see Julie, so hopefully it looks okay. Okay, thumbs up. Wonderful. Okay, thank you, Julie. Thank you all for coming. So I will be giving an update on behalf of the Galactic Bulge Time Domain Survey Definition Committee, which I'm co-chairing with Jesse Christensen. We've been hard at work for the better part of this year to define what will hopefully be a diverse and very successful core community survey in the Galactic Bulge, one of the 3 surveys that Roman will perform as part of its main mission. So I will be giving an update on where the committee stands. I'll give a little bit of an update on the timeline, but the main goal here is really to give you, the community, an idea of which ideas that we've received from the community through white paper calls and other calls we're currently leaning towards implementing into the report that we're writing up for the Roman project, which will be due in November, as to what the survey will actually do and what science it will enable. So I'll start off with just a reminder about the Roman observational program, given that this audience here is probably a bit broader. So as a reminder, a significant chunk of time, 75% of the time of Roman, will be spent on very large surveys called the core community surveys. Those will be the majority of the time that Roman will spend, and they are subdivided in sort of 3 broad surveys and 2 broad science categories. One is dark energy, which will be covered by the high latitude wide area survey and the high latitude time domain survey, both of which have cosmology goals. And you will get updates at different times from the respective chairs of those core community definition committees at another time. And the other one is exoplanets, the main science driver for the Galactic Bulge Time Domain Survey, which is the one that I will be talking about today. So these 3 surveys make up what's called the core community surveys that will enable broad astrophysics with wide field infrared capabilities that Roman brings to bear. In addition to this, there will also be general astrophysics surveys that will be solicited through the community through proposals that will be made available, or the first call for proposals will be in October 2025. There's another survey that has already been, or is currently being defined, that has been selected as part of the early definition community call, and that is the Galactic Plane Survey. But everything else, all the other general astrophysics surveys, will be selected through the regular peer-reviewed process. And of course, there's also lots of archival investigations that will be done using Roman data, given that all the data will be public immediately. In addition to this, there's also chronograph technology demonstrations that will happen as part of the Roman observing program, but that's not using the wide field imaging instrument that we'll be talking about for the core community surveys. So graphically, I guess, to show the core community surveys, right? So we will be talking today about the Galactic Bulge Time Domain Survey, which will basically perform time domain observations of a few square degrees field of view near in the Galactic Bulge. There will be two other core community surveys, as I've already mentioned. The wide area survey that will be basically doing multi-band imaging and slit-line spectroscopy of a very wide area, thousands of square degrees. And then a smaller area time domain survey of tens of square degrees for supernova cosmology. That's the high latitude time domain survey. And then in addition to this is the Galactic Plane Survey. So this is has been more recently decided on, and the committee for that is now formed and meeting to define a survey that will basically perform imaging in multiple filters of the galactic plane. So it's important to distinguish those two. There's the Galactic Plane Survey and there's the Galactic Bulge Time Domain Survey. And the main way to sort of think about distinguishing them is that the GBTDS has a time domain component, right? So it's high cadence observations over several weeks, as I'll talk about in a second, versus the Galactic Plane Survey, which is mostly imaging a wide area of the galactic plane. Okay, so to get into the committee, so we're one of the 3 core community surveys, and we have a committee from 10 community members, which you see here. So Jesse and I are the co-chairs, and you see the other folks who are serving on the committee here. We have a diverse range of science expertise that serves on this committee, and that's of course because the Galactic Bulge Time Domain Survey can enable a very diverse range of science, and so we've drawn from the community, and we have folks with expertise spanning all the way from exoplanets to stars to galactic astronomy to extragalactic astronomy. We also have, in addition to the folks where you see pictures here, we have 2 liaisons to the solar system community who are joining both the meetings of our core community survey as well as the others. So both Susan and Rosemary are sort of like joining all the different core community survey meetings and provide feedback for science interests for the solar system community. Okay, so as a reminder, the Galactic Bulge Time Domain Survey, like other core community surveys, have science requirements. And the science requirements for the Galactic Bulge Time Domain Survey surround exoplanets, and in particular, exoplanet demographics using microlensing. So Roman will essentially, as part of this core community survey, carry out a census of exoplanet systems in our galaxy using gravitational microlensing, which opens up a very new parameter space in terms of exoplanets' masses and semi-major axis. So this is shown in this graph from Matthew Penny's work in 2019, showing the mass of the planets in Earth masses versus the semi-major axis, and showing the known population of transiting planets that Kepler has uncovered. But of course, the transit method is very heavily biased towards short orbital periods, so small semi-major axes. And so Roman, back then still called W first, will of course fill this gap through gravitational microlensing, which has very strong sensitivity at much larger semi-major axes, and in addition, also very low masses. So that's basically the science requirement, and each of these core community surveys have these science requirements. So we basically, the definitions that we're making have to be around the main science requirement of the core community surveys. So you can define these science requirements more specifically, and they are, of course, defined very specifically. And so there's a lot of text on here. I won't go through this, but these are essentially the level 1 requirements for the Galactic Bulge Time Domain Survey in terms of exoplanet microlensing. The main thing to take away from this is that 4 of these requirements refer to yields, or basically occurrence rates of planets of various masses, and one of them refers to the measurement of masses of the planets themselves. And so this particular requirement of actually measuring the mass of a planet through microlensing has additional requirements of actually making it possible. And so when I get into the points of how the survey actually looks like, for example, doing multiband photometry, that is driven by the science requirement of measuring the masses of some of the planets that are discovered. And there are white papers that have provided a lot of feedback and detail as to how these science requirements can be implemented and can be met using the current sort of draft implementations of the survey itself. So just to give some boundary conditions, I guess, in what the committee is actually working with. So each committee, including ours, works with the science requirements. So we cannot change the survey completely. We can change things and implement things while still having the survey meet its level 1 requirements. So as a reference survey, and there have been many before, we start by basically taking Matthew Penny's work from 2019 as a reference survey. And so that reference survey of how the observations actually look like propose 72-day observing seasons. So there will be 72-day observations of 7 fields near the galactic bulge. So each one of these is a field, a Roman field. So what Roman would do is he would observe one field, hop to the next, and so on and so forth, and then repeat this pattern for 72 days each. By slewing from one field to the next, the cadence that would be reached with a broadband filter would be about 15 minutes. So you get 15-minute cadence over 72 days in a roughly 2 square degree survey area. And we do this 6 times. So there are 6 seasons in which these 72-day observing campaigns will be performed. And again, the main sort of there's a high cadence, which nominally is 15 minutes, that will be performed in a broad filter, but there will be a lower cadence mode as well with a narrowband filter, and that has its reasons related to the mass measurement requirement for exoplanet microlensing. So this is sort of the reference survey, one of the reference surveys that we can take, and then we can sort of think about what sort of deviations that we can implement from this reference survey, this 6 times 72 observing seasons, 7 fields, 15-minute cadence, 12-hour cadence with another filter. And so the changes that we've been sort of broadly considering, actually we can't change it completely again, but we can change it somewhat, are as follows. So for example, you could change the length of the observing seasons. You cannot go much longer than 72 days. That's an observatory requirement, but you can of course go shorter. So you could do observing seasons as short as 60 days and as long as 72 days. You can't go much shorter than 60 days because that will then severely impact the yield for exoplanet microlensing. You can change the number of fields observed in each seasons, right? So in the nominal sort of reference survey, there's 7 fields, but of course you can decrease that. You can have less fields with higher cadence, or you have more fields with lower cadence. So these are, of course, and I'll get to that in a bit more detail later, related to each other, right? So if you add or decrease the number of fields that you're hopping over, then that will affect the cadence of the observations. And then also the cadence of the narrow filter or filters, which could be multiple filters, that can vary on the order of something like 3 to 12 hours. In the nominal reference survey, it was 12 hours that was assumed. So we've received community input from the community, which is one of the main things that the committee has been working with. So there were about a little bit over 20 white papers and a little bit over 40 science pitches that were submitted by the Roman project and that the committee used as input. We have, these are, by the way, word clouds of the submissions, which basically gives you an idea of the diversity of science that the community wants or suggests that Roman can do with the Galactic Bulge Time Domain Survey. So this is, of course, includes exoplanets, but also variable stars, stellar physics, binary stars, all kinds of science that can be enabled by a time domain survey with a very wide field of view. So we used this as input in the committee to review the ideas that came from the community. We also sent a follow-up call for updates to the authors of the white papers earlier this year, because there was a little bit of a time delay basically between when the community input was collected and when the committee actually ramped up, when we ramped up our work. So we had a follow-up call to the white paper authors. But this was really the main sort of input that we've started with at the beginning. So a little bit on the timeline. So the committee formed in February this year. We then designed and organized a review process for the white papers and for the science pitches. We reviewed them, we ranked them, discussed them in broad science ideas. So this wasn't necessarily going with like, oh, this white paper ranking over this white paper, but we sort of broadly collected common science ideas that were proposed by the community through the white papers, and then ranked and sort of prioritized these science ideas rather than individual white papers. So that happened in the first half of this year, and then throughout the summer, basically we've been mostly focused on really the community interaction and feedback and reporting to the community, as we're doing here. So we did this at the Roman Science Conference in Pasadena that happened earlier in July. We had a Roman Community Forum. We gave a similar update, and then we're of course here at the virtual town hall. I want to emphasize that we're still looking for feedback, in particular from folks that haven't given feedback before, right? Maybe you weren't part of the white paper call or the science pitch call, and you weren't able to join the other opportunities that were there. So if you're joining, for the first time and you hear about this for the first time and you have thoughts on any of the things that we're presenting, we'd love to hear from you, and I'll end the talk with how to do this. We have several resources and how we can get community feedback. The reminder of the time that the committee will spend is basically refining some of the sort of decisions that we've made, and looking into the simulations, the trade studies, and actually implement some of the survey ideas that we'll have. I'll get into detail on this in a second. We probably want to have one more sort of preview of the actual survey definitions to the community, and then on November 1st, in fact, is our report due to the Roman project. So there's a short fuse now, and we're working very hard to pull it all together, including the feedback we get from the community. Okay, so what I'm going to do now for the remainder is to go through some of the ideas that the committee has considered, and I will give an indication on whether this is likely something that will end up in the implementation of the surveys that we'll recommend to the Roman project or not. So I'll sort of have likely modifications that the committee is really leaning towards implementing, possible modifications that we're really looking into and trying to make work, depending on more work that needs to be done in terms of simulating the impact, and ideas that we've considered but are probably more likely or more suitable for general astrophysics programs rather than the core community surveys. So one of the things that we have considered is to add a field at the galactic center. So the nominal fields, if we think back to the slides that I showed before, were sort of off-center from the galactic center, of course near the bulge, but a little bit below in galactic latitude. And so there were several white papers that have suggested to add a field at the galactic center and make that part of the galactic bulge time domain survey. This has a lot of science implications. Two of them are shown here from two white papers with references given. One of them is that it will increase the overlap with known X-ray sources. So the plot on the left here shows in green X-ray sources identified by Chandra. So that will allow basically studies of energetic sources such as CVs and X-ray binaries, both using time domain infrared photometry. And on the right is that one of the big science cases that you can enable is to actually study stellar populations in the galactic center. So this is the stellar density as a function of the distance from the galactic center, showing the different populations in the galactic center, the nuclear star cluster, the nuclear stellar disk, that make up the stellar populations near the galactic center. And Roman's large field of view really is very powerful here. It allows you to basically, in a single pointing, get a very large fraction, right, of the stellar populations that surround the galactic center, a factor of 7 more than was possible with Roman, that includes some younger populations as well, such as the arches and the quintuplet clusters. And so you can study these populations both using photometry, but also, of course, using kinematics. There's additional science. There are, binaries, stellar compact object binaries, variable stars, perhaps even transiting planets that you can find near the galactic center. That all would be enabled by adding an additional field. Okay, another possible modification that we're considering is to speed up the cadence, faster cadence. So remember the sort of nominal reference survey we're working from was 15 minutes, so have a 15-minute cadence. There are several science cases that would benefit from doing this quicker. One of which is transiting exoplanets. There's actually a lot of work and a huge amount of expected yield of transiting exoplanets that just basically come from the fact that we're having a time domain survey of lots of stars. So this is from Robbie Wilson's white paper showing the relative change in planet yield as a function of the cadence, basically, of the observations, subdivided by the size of the planets. And basically, the faster the cadence is, the more sensitive you will be for smaller planets, in particular sub-Neptune-sized planets. There are also general stellar astrophysics cases that would benefit from this, including astroseismology of red giants. So red giants pulsate on timescales that are accessible to light curves that are sampled with 15-minute cadence. But if you increase the cadence, you essentially increase the signal to noise to the point where the yields will substantially benefit. So these are simulated power spectra of oscillating red giants, showing the difference between a 15-minute cadence. So these are two stars, one in blue, one in orange, and one in 15-minute cadence, and one with 7.5-minute cadence. So if you just double the cadence, your signal to noise will increase substantially. And that might actually be quite important because the current detection limit is around the red clump, so the helium core burning stars, of which there are many, and so faster cadence would definitely make sure that we can catch these stars. Of course, this requires balance between with adding more fields. There's also, I should mention this, there's also arguments for the microlensing case, in fact, to have faster cadence, in particular for free-floating planets. And there was a recent white paper by Andy Gold and collaborators that pointed that out. So faster cadence also has a substantial impact in microlensing planet demographics. So all of this, of course, needs to come at a balance, right, with adding more fields. So we're thinking about modifications to this rather than just doing all the fields, or cutting the fields in half and doing everything twice as fast. Maybe there is a variation to this where you do one field twice as fast and compensate for it for observing other fields at a slower cadence, or perhaps a pointing strategy where we have fields that are actually overlapping. And that would be another way that you could achieve faster cadence for some part of the entire footprint of the field. So rather than doing the whole 2 square degrees with faster cadence, currently we're exploring mechanisms that can achieve faster cadence, but only for a subset of the fields, while still keeping the footprint of the survey large enough. Okay, so there were a couple of suggestions, white paper suggestions of very exciting science that required a bit of longer slews to get to points that would be added as an additional field. So one of those is, for example, the idea of observing a globular cluster with Roman. There's lots of exciting science that you could do in a time domain sense with getting time domain photometry of a globular cluster. That's, of course, stellar astrophysics, astroseismology, rotation, transiting exoplanets. So that was suggested in a couple of white papers. Shown here is, again, the nominal Roman pointings as well as the positions of some globular clusters that could be added as an additional field. There was another suggestion of adding a field for a little bit further along in the so-called Earth transit zone. So those are basically targeting stars that can see the Earth transit in front of the sun. So the main science motivation here would be to detect transiting planets around stars where stars can actually see the Earth transit as well. It turns out that the Roman field of view is actually exquisitely matched to this very narrow sliver along the ecliptic plane where this can happen. These are modifications that will, at this point, unlikely to be incorporated into the draft surveys. We're still looking into the globular clusters. The main reason for this is that the slew times to get to these fields would be probably prohibitively expensive, and I'll show why that is in a second. So again, these are sort of great ideas coming from the community. Some of these, maybe both of these, all of these, can be implemented hopefully through a general astrophysics program, but currently we're not considering them as options in the implementation of the Galactic Bulge time domain survey. So one of the reasons why this is hard is the trade-off between cadence fields and exposure time. So basically, once you set 2 of these, right, the other one is fixed. So Matthew Penny has done some simulations to demonstrate this. where you have different pointing strategies. And if you assume that you fix the exposure time to, for example, 50 seconds, which is a nominal number that I've been using, of course, depending on what value you assume for the exposure time, the depth will change. But if we assume that we have a fixed exposure time, which is more or less fixed by the microlensing yields as well, we can then explore what different pointings do to the cadence. And this is what's showing here. So this is a nominal field where you have 7 contiguous fields along the galactic bulge near the area that I've shown before. And using this, we've updated SLU several times for the observatory, you get about a 12-minute cadence. If you would say, okay, we need more fields, so we have 9 contiguous fields near the galactic bulge, you would get about a 15-minute cadence. If we say that we want 7 fields plus the galactic center, so this is the option that we're currently strongly considering, right? You hop between the fields and you do one hop that's a little bit further towards the galactic center and then back. That gives you a cadence of about 14 minutes. But if you, for example, implement a longer SLU field, such as the Earth transit zone, 7 contiguous fields and the Earth transit zone, you quickly get to numbers for the observing cadence that exceed 15 minutes. In this case, it would be 17. And so the cadence is a really important requirement for the exoplanet microlensing yield. And in general, things that go well above 15 minutes are probably prohibitively expensive in terms of sensitivity. So this is one consideration why, at the contiguous fields, adding 1 field is possible, 2 is probably too more expensive, and 1 field that's far away is probably also too expensive to implement. Okay, so one other likely modification that we're considering are off-season observations. So these are observations that happen not during the seasons where we get high cadence observations. So Roman will observe for 5 years. So there will be a total of 10 seasons where the galactic bulge can be observed. The current strategy is that the high cadence seasons happen at the very beginning and at the very end. So 3 seasons at the start and 3 seasons at the end. This is because you want a long baseline for astrometric measurements. And so there have been several suggestions in the community to add lower cadence observations in what we call the off seasons. So the seasons in between that are currently not used, the 4 seasons that are currently not used. And the main motivation for this is to catch microlensing lensing events that have longer durations. So for example, if you increase the mass of the object that does the lensing, such as isolated black holes, you get a substantial increase in the duration of your lensing event by about a factor of 100. And once that happens, right, you can be in the situation where you have a lensing event and you would completely miss it if you only observe at the start and only observe at the end. Of course, you don't need the high cadence to catch the planets through microlensing, so low cadence observation are actually just fine to do this. So possible cadences that are suggested is 1 observation per day, 1 observation every 10 days. We're currently investigating what the best trade-off is. These would likely not be strictly periodic, but they don't have to be as well. There have also been recent suggestions for a white paper to actually move 1 of the high cadence observations to be more central, or maybe 2 of them to move them more central rather than have them free on each side. That's a variation that would achieve a similar goal. But mostly we're currently considering the off-season low cadence observations for enabling these science cases. Okay, some other modifications that are likely and that are new are that we are considering implementing multi-band photometry observations as part of the Galactic Bulge time domain survey. So the wide field imager has many different filters. The main filter that we'll be using, right, for the high cadence observations is the broad filter, and then maybe 1 or 2 narrowband filters to support the microlensing mass measurement requirement. But in addition to this, there's an idea to just basically take an image of all the fields that we will observe in all of the filters. And that has, of course, advantages for deriving colors of stars, deriving temperatures, stellar characterization, or just characterization of the sources in general, right? If you have multiple filters, you can build up SCDs and measure colors of objects. An even more bold variant of this that we're currently looking at is to actually observe each field with spectroscopy. So the low resolution spectroscopy modes that Roman offers, in particular the R500 mode through the GRISM. So these would be observations that are, of course, challenging because of the crowding. Hans-Walter Rix on the committee and collaborators are currently looking and working on how this can actually be implemented. And initial results look quite good, that you can actually have substantial success in disentangling spectra. So these are slitless spectra, of course, that overlap in the crowded fields. But there is actually the good chances that these can actually be disentangled, to the sense that we can extract very valuable information such as temperatures, radial velocities of these stars in the fields. So these ideas can be done either once at the beginning and end of the survey, or with some kind of low cadence throughout the seasons. This is still to be worked out, but this is something that we're currently considering as well of implementing in the surveys. Okay, another possible modification is to observe one field at very high cadence. So this currently, right, we've considered sort of the 15-minute cadence and then a variation that goes a bit faster. This would be an idea we just stay on one field and do very fast cadence observations. There are science cases that would benefit from this, for example, short period eclipsing binaries, as well as a very different science case, which is the detection of gravitational waves through astrometric measurements that require sort of deep image stacking. The short period eclipsing binaries is one that could potentially be achieved even without high cadence observations, due to the fact that the observations that we're taking regularly during the 15-minute nominal observations are not strictly periodic. So it's possible that some or maybe most of these EBs can be picked up that way, even without a dedicated 1-minute cadence campaign. So this is a significant investment. If it's something like, a 1-day observation every season, that would be a significant time investment. And again, maybe better suited for a general astrophysics program. So this is a possible modification. We're still sort of working out the details, for example, of whether there's a scenario that would give important insights in, for example, the gravitational wave detection case, that would drive this to be included into the survey definitions. Okay, and then finally, a couple of things that do not require modifications, at least yet, from our committee. So one of them is synergies with other surveys. This has been pointed out in multiple white papers. There are excellent synergies that can be achieved with Roman and other surveys. One of them is, of course, Euclid. There's lots and lots of reasons why this would be a good idea, to do simultaneous observations with Roman and Euclid, perhaps even precursor observations with Euclid of the Roman fields. There are, of course, also benefits with ground-based observations, so synergies with ground-based observations such as Rubin. So here is an example, for example, observing a lensing event, both from the ground and with Rubin and with Roman. So currently these do not have an impact on the survey design, but it's important to keep the flexibility to enable and support these synergies. And our goal as the committee is to write this in the reports to make sure that the Roman project keeps this flexibility as much as possible to support these synergies, which are clearly very important. And then finally, there's a white paper on the readout schemes in terms of how the readout will work on Roman. So this is something that we're also have discussed. We're not actually at the point of the implementation detail yet. The basic science case here is that very short duration events such as flares can be captured better if the readouts, so basically the individual reads, which are the points here, the way that they are combined into resultants, which are actually then analyzed, if the way that they are collected is not even, so you basically have even resultants that just take individual reads evenly. If you have a scheme that results in that uses uneven resultants, that gives you a better way to characterize short duration flares, as shown here. So this is one flare, for example, that the coverage you would get with Roman in the case of even resultants and with uneven resultants. So this is something that we're aware of, and we will be. I think there's not a lot of reasons not to implement this that way, but we're aware of it, but we're currently not at the stage of implementation yet where this has become very relevant. But I think, in fact, the uneven resultants is the default way that this is currently being thought of within the Roman project as well. Okay, I want to finish up with just giving you a preview of sort of the way that we're currently thinking of putting all this together. We're actually tasked, our charge is to recommend 3 different survey designs. that basically add up to different total amounts of survey duration. So an underguide, which will add up to 380 days of total survey duration for the Galactic Bulge time domain survey, a nominal survey, which will be 420 days, and an overguide, which will be 20 days more. So one possible way that our current working sort of structure for this is shown here. So this is preliminary, but it is sort of getting firmer as we move towards the November date. So for example, for the nominal survey, so that will be nominally if you get 420 days, that depends on balancing the requirements with the other core community survey that will be carried out. We would be performing 6 times 70-day seasons, including the Galactic Center. So this would be 70-day observing seasons, 6 times, that will add up to 420 days, but we include the Galactic Center. And we add some very low-cost additional observations, such as the multiband imaging and the spectroscopy of the fields as well. But those take up so little time, especially if we only do it once or twice, that they don't really factor into the total duration. Then, of course, the underguide would be a minimal strategy where we want to get as long as possible on the seasons. So we would be something like 6 times 63-day seasons, or however long as possible, with contiguous fields only. So no Galactic Center here, and the reason for this is that we want to have faster cadence to support as much as possible the microlensing science requirements, and to make sure that those science requirements can be met. And that will be better met if you have contiguous fields, because that will give you faster cadence. And perhaps, one low-cost idea, such as implementing the imaging in multiple bands. And then the overguide could, of course, include a lot of things, including some of the things I've talked about. That includes the 72-day seasons, so the longest possible seasons we can do, the off-season observations that we have mentioned, including the Galactic Center in the seasons themselves, the off-season observations, the high cadence observations, so perhaps a 1-minute cadence observation for some amount of time in each season, and then the extra multiband and spectroscopy observations that we've mentioned before. We're currently considering sort of what would be required to move the off-season observations from the overguide into the nominal case, given that there's a sense that these are quite important, would enable a lot of science, and it would be good to have these fit into the nominal survey design as well. So our current work is basically simulate the impact of all of this on the exoplanet yields. That's really important. We cannot define a survey that breaks the level 1 requirements. So we're currently working, and this is led by Matthew Penny, and the project infrastructure team is working on sort of quantifying what these changes do to the yields for the exoplanet microlensing, and then the final recommendations will be made based on those results. Okay, science enabled by the Roman GBDDS is vast. I thought about the sort of science that's being enabled by the things that we're planning to implement, and I concluded it's basically the word cloud that you've seen at the start from the white papers. There's not much that you see here in terms of words, I think, that will not be enabled by the Galactic Bulge time domain services. There's a huge amount of science that will be enabled, including by the considerations for the definitions that we're currently considering. Okay, so I want to wrap up here. I think I've talked a little bit longer than I should have, by saying that we would like to, of course, have the community's feedback for all of you here. There are 2 ways to do this. Obviously, one is the Q&A that will follow right after this, but there's also a questionnaire that the project put together where you can leave your thoughts. The QR code is here and the link is here directly, or you can, of course, also directly email me and Jesse with your thoughts on anything that you've seen here today. Okay, I'll stop here. Thank you.
Thanks, Dan. Looks like Jennifer Yee has a question.
Yeah, hi. Thank you. I actually have 3 questions, or 2 questions and a comment. When you're talking about slide 13, you were giving cadences for the trade-offs for the cadences in the field. Is that using the latest on the slew and settle times? Because I know they've been improving over time.
Yes, the answer is yes. So this is using the latest updates that we have from the Roman project on the slew and settle times. So I think this is the main reason why this is 12 minutes and not 15 minutes, as
Okay.
it was in Matthew's earlier simulations. But yes.
Also about this, I'm really intrigued by this idea of doing the galactic center fields. The science cases sound very exciting, but I'm wondering what's the driver for the cadence of that galactic center field? Like, does it need, is the science there driving this 13-minute cadence? Or, for example, if you could tolerate a lower cadence in the galactic center, could you then apply that to increasing the cadence of one of the other standard microlensing fields to achieve that increased cadence thing with the...
Yeah, the cadence driver is, I mean, if you think about stellar astrophysics, for example, so seismology would need the cadence the way it is with the other fields as well. The stellar population side, right, the kinematics and the general stellar variability of stellar populations probably don't need as fast of a cadence. And I believe in the white paper from that put that science case forward. So the Terry et al. White paper, they have a version, a minimal version, right, of having the galactic center that does not have the same cadence as the remainder of the fields. So there is a minimal version that sort of gets you some of the science in terms of studying the stellar populations in the galactic center that doesn't require a 15-minute cadence. I think the general sense currently is that having the same cadence would enable more science in the galactic center than it would if we do a slower cadence, but it would need, it has to be balanced. So for example, if if the simulations come back from the microlensing yields and they say that, adding the galactic center will result in a cadence in the nominal fields that will not give us the yield that we need, then that would be one backup plan, absolutely, where you would say, we include the galactic center, but we do it at a slower cadence to the benefit of the other fields that get higher cadence and thus, enable the level 1 requirements. Okay. So it's certainly something that's considered. I think the likely modification here, as stated, is I think it's very likely that we'll recommend a galactic center to be added. Whether that is at the nominal cadence or not, that's still an open question.
Okay, and then the last thing was that I'm not entirely convinced that the uneven reads are net neutral. For other science. They seem very tuned to things that rise fast and fall slowly. And in microlensing, we get them both ways. So it's just something to think about for a hot second before making that decision. Just declaring that it's totally neutral to everything else.
So maybe Tom can weigh in on this a little in terms of how the nominal plan actually is. Maybe I misspoke by saying that the uneven resultants are the nominal plan.
No, that is the plan, Dan. And so the reason to do an uneven sampling of the is because that way you get greater dynamic range. It's because if you have high sampling when you start the ramp, you can get data on bright things before they saturate. Right. And then and as you have less dense sampling, you can get those extra samples and increase that signal to noise for the fainter things.
Okay. All right. Well, that sounds better then. Okay, thanks.
Yeah, I forgot about the bright stars. Yeah, but it would be interesting to hear. I mean, if this is something that actually affects microlensing significantly, I don't think we've considered that yet. So if that is actually something that would have a substantial impact, it would be good to hear more about it.
It just flares are different from microlensing, so
yeah, yeah, absolutely.
It's just thinking about that. Okay, thank you very much.
Thanks, Jennifer.
I see hands from Sanjib Sharma.
Hello. Yeah, I was just wondering, so you talk it's a 60-day season, and as I understand, there are constraints on the roll angle of the spacecraft. It has to be within plus minus 15 degree of the maximum solar power thing. So is it possible to maintain the orientation of that field over the 60 days? Have you thought about this, or am I overthinking?
This is Jeff. The answer is yes. You can keep it fixed, in fact, for the whole 72 days.
Okay.
It's close enough to the ecliptic that the spacecraft roll changes very little.
Okay. Okay. So it depends upon where you're looking. Okay.
But I think the upper limit, right? The 72 days is an upper limit that's related to spacecraft constraints. Is that right, Jeff?
Yes,
Well-
that's thermal. We can't extend the
Thermal.
pitch angle of the observatory more than that.
Okay, Tom, I'll let you moderate unless you want me to.
Yeah, go ahead. Bob Benjamin was the next person.
Yeah, hey, so this looks really great. I really like the galactic center field too, obviously. But my question is, in terms of the number of filters, is the reason you want to do all the filters because you need all the filters, or is it just because it's so cheap that you might as well just do them all because they might come in useful?
Yeah, it's more the latter. I mean, it's I think, you know, it's additional information that is probably not crucial for any one of the science cases, but it is cheap enough to do to roll through the filter wheel and take one image of all the fields at least once, right? To characterize the sources that are in the field. And this can be this can be very, very cheap if you only do it once. Of course, you may think of science ideas where it becomes more expensive if you do it more than once and you do it every season, or you do it with some kind of cadence. I don't think we're considering it at that level. But just measuring, you know, colors of objects in these fields will be well studied for a very long time, and just having color information from all the filters seems like a relatively cheap thing to do that, you know, is not very time intensive, but could have, you know, a lot of science benefits for various applications.
I agree. I just wasn't sure if there was any science driver other than we know that we'll want to know those fields in much detail as possible going forward.
Yeah, there's not a single science driver for it. It's more about supporting, you know, doing something that is relatively cheap on time and has obvious benefit for supporting other science cases. The same is true actually for the Prism idea, right? Which is that, you know, just knowing the stars better in each of these fields would be really, really valuable. And so if you can get a way to get spectroscopic information, because we can, I mean, the instrument is available, that would be really good. Like, for example, velocities, right? It would be tremendous if we could measure rate velocities of all the stars in all those fields and then combine it with the time domain data that we get from the nominal survey.
Thanks.
And Sean Terry has a question.
Yeah, just a quick response actually to Jennifer's question about the cadence for the GC observations. Actually pulled
Yeah,
up
go ahead, Sean.
because
I'm glad you're on. I didn't see that you're on, so I should have just directed to you to answer that question.
Yeah, I forget some of the details, so I pulled up the white paper myself. But so there are tables in that paper about so we did a minimal and an optimal sort of observing cadence. So minimal would be every 12 hours and only one filter. And so, you know, there's several science cases that are sort of optimized, but I think the two that are most, you know, optimized are the monitoring of Sagittarius A star itself. So there's been studies in the UCLA group, the Galactic Center group has found very high cadence flares in the near IR on Sagittarius A star. And then also transiting exoplanet case has sort of benefited quite a lot with a cadence that's the same as the nominal GBTDS. But there's all the details are in that white paper.
All right. Joel Zinn.
Thanks so much, Dan, for the overview. To piggyback on some of the Galactic Center stuff, I'm wondering why in the last slides, the recommendation or the nominal case for including the Galactic Center seems to be for 6 fields instead of 7. Is that again to increase the cadence of the non-Galactic Center fields? And to follow up on that, what is kind of the understanding of what the cadence is required to be on the exoplanet side because I thought that 15 minutes was okay.
So if you're referring to the number 6 here, so that's the number of seasons, right? Rather than the number of fields.
Oh,
So
gotcha.
this doesn't say anything about what we do within a season, how the season itself, well, it says a little bit about it, but it says, the information about what we do within a season is basically including the galactic center or not. So having only contiguous fields or doing contiguous fields with the galactic center. It doesn't specify yet how many fields there are. Right, so this would just be 6 seasons, 3 at the start, 3 at the end, and then during those seasons doing some number of fields plus the galactic center that will result in a predicted yield for microlensing exoplanets that achieves the level 1 requirements. Right, so nominally that would be something like 7 contiguous fields plus the galactic center, which the simulations currently show would get us a cadence of 14 minutes or so. But yeah, so the 6 here is basically, how often we go to the bulge.
Thank you.
And that is, that number that follows is basically just maximizing however long the each individual case is, right? So 6 times 70 is just having 420 days. But the cadence is for exoplanet transits and for microlensing, both would benefit from faster cadence, right? So this was sort of the point in Robbie's paper about the yield of small planets, and in the recent white paper that Jennifer was part of that pointed out that the population of free-floating planets would be much better recovered if you actually increase the cadence. So there are many considerations of going faster with the cadence, but it has to be sort of balanced against decreasing the number of fields and how to implement it. But that all currently is still a bit up in the air, and it's basically awaiting simulations that the PIT, the project infrastructure team, and Matthew Penny in particular are implementing. But I think the best current way to judge from this is that we'll try to do some compromise between the two, which may be this overlapping field idea, where you get some higher cadence for some fraction of the fields, but not all of them.
Thanks.
Does that answer your question?
Yes.
Okay, I don't see any more hands, but we certainly have time for a few more questions if there are any. Michael.
Could you say more about what makes the GRISM observations of the crowded fields feasible?
Yeah. So Hans-Walter Rix is just reported on this, I think last week when he had a telecon. But the basic idea is that you have a very crowded field and you have lots of spectra that overlap. But if you assume that the spectra of the stars are simple enough, you can sort of treat it as a linear eigenvalue problem where you have a very crowded field, but if you model the stars in low resolution and decompose them as a sort of linear problem where you say 1 pixel is the superposition of many stars of low resolution spectra, as long as they don't spatially overlap and the spectroscopic information, so the lines don't overlap completely, there is a way to back out information, rough information about temperature, metallicity, and velocity. I don't think we can hope for much more than that just because of the low resolution. But the crowding itself appears to be solvable if you basically model the data as an ensemble, right? So you model, thousands of stars in a given part of the detector where the spectra are overlapping. So that's about as much information as I can give, I think, based on my point of view. It's still very active, actively being looked into, but initial results look promising. And I think there's also another group who has looked into this apart from Hans Walter that found similar results. So it's not as hopeless as it might seem just looking at, you know, an image of slitless spectra that are completely merged together. Because if you use techniques that, you know, make some simplifying assumptions, you could actually back out information about the spectra of the stars themselves. That probably wasn't a very satisfying answer, but I would direct you to Hans Walter for more details on it. Initial results look probably. I was a bit skeptical too, and I think when we were at the Pasadena meeting, folks were fairly skeptical. But it looks like it might actually be quite feasible to do this. Again, this is an idea that, you know, in its simplest form would be very little actual time from the bulge survey. That would, if it works, right, would provide a lot of benefits to other science cases.
And Joel?
Unrelated question, more along the lines of these lower cadence proposed observations in between the high cadence ones. What is the trade-off that's being considered there? I mean, what is that time being taken away from? And yeah, I guess that's my main question with that.
Yeah, very good question. I think it depends on what the cadence is, right? So this could actually also be a fairly cheap thing if you do it one every 2 days. Sorry, one observation every 10 days. It would actually not take away a lot of time from the other, you know, from the main survey fields. If you increase the cadence sufficiently, right, then it would actually start to become a bit more expensive, and it would probably eat away a bit of time from the duration of the individual seasons. Forget which way we actually had it lined up here. So, right, so if you do it the way that this is currently laid out, so you have 6 times 72 seasons, you're left with 8 days in the overguide, right? Where we can do other things. And that is basically that, you know, in that scenario for the overguide, that would probably be mostly spent on higher cadence observations of the off seasons. In the nominal scenario, that would probably not be possible because we'd have to focus on the low cadence observations, on the high cadence observations in the nominal fields. And so in that scenario, you would get a much lower cadence in the off seasons. But the off seasons don't really need you know, a very high cadence. So it depends on what you're trying to achieve. But that's where the trade-off comes from. I think from all of these ideas, right, these 3 or these 2, which is the off-season observations and the high cadence observations, are the only ones that really would take a significant bite out of the seasons in the nominal case.
I see another question, but before we jump to that, and because some people might be leaving the call, I just wanted to remind people that Ori put in the chat a link to a survey to provide feedback, and you can also email Dan and the other chairs about this. We have meetings like this. We have 2 more this week. And there's another Galactic Bulge meeting next week, done at 10 a.m. East Coast time. And there was just to remind people that those interested in the status of the Wide Field instrument, we have a community forum this Wednesday afternoon at 4 p.m. Eastern, which provide lots of updates on and images coming from our flight detectors. So please join us for that. So I think so. I see a question from Sean.
Yeah, just I'll be extremely fast. Just Dan, you had a slide about synergies with other surveys. So just a very quick shameless plug. There's a very, very new large HST program that was accepted for cycle 32. So it will image quite a substantial amount of the GBTDS fields. So sort of precursor imaging.
Nice, wonderful. It's great to hear. Yeah.
Yep.
Thanks, Sean.
Okay, I don't see any more questions, and we're at 8 p.m. And Julie, did you want to say anything to close us out?
No, I think this was a great discussion. Delighted to see so many questions and comments, and looking forward to continuing to progress the definition of these surveys. Thank you.
Thanks, Dan. Thanks, everyone.
Thanks, everyone.